Okay, so this is the second part. So this is basically the lab tutorial for laboratory number 1, which is about the signals. And well, I kind of took a risk that well, you haven't taken a look at what kind of notes I have there. So I just quickly draw what this exercise is all about. There. So the first exercise is actually about sampling. It's about sampled data. So we have a analog signal, and how to make it sample signal, you just have a sampling rate. We define the sample time, which is basically just sample time is 1 over fs. So it's the time difference between two samples, and then you basically do the just take the snapshot of the signal on those times. Quite simple. So if you have x of t, then basically that becomes x of n, simply x at time n time ts, where this n is just the index, sampling index. Okay. So sample data is nice, since then you can put it on table on computer. Simple. Good. There's a couple of fundamental signals that we play with there. One is the units of impulse function. Another one is the unit step function. So basically, if you need a simple one peak somewhere, you would use a unit impulse function. And if you want to, for example, start a signal somewhere, then you would multiply the signal with the unit step function. For example, if you have a any analog system, then to test this analog systems, you would need the analog edge there, or a square wave, something like that. So you would generate it with unit step function. And in output of your Sound Blaster or whatever your digit or your D2A converter, you would have that kind of edge. Then you can actually calculate the system step response that you can sample, that you can then analyze on the computer to see if it actually fits into your theory. The same things what you probably did on the first year classes of the signals. Right. Okay, so today we are going through that stuff, how to generate different kind of data sets on the computer, and also how to make them look quite, say, natural by adding some noise into it. Good. So that's the short version of the theory. Would you turn off the lights? Someone. Anyone. All right, so exercise tutorial. So I will just go and take a look at what should be done in here. Index vectors. And so on step functions, good. So basically, next I will start the MATLAB. Okay, MATLAB is our standard program because it's used quite a lot in industry, especially if they are doing anything serious about the digital signal processing, then they have MATLAB. That's the industry standard for. Maybe also the last slide. Let's see. How come the... Oh, that's great. I see. There's the light switch also here. Good. So that's the MATLAB. It looks like this when you open it. It's not necessarily on the workspace, but anyways. Did anyone have trouble finding it? No. Okay. You just search MATLAB and that's it. How many of you have used MATLAB before? Everyone? Or even this must. This also counts. Okay, good. So it's basically an old-fashioned command-driven program which is designed originally for handling of matrix information, but later on it has become an industry standard because of all of these nice extra packages. For example, if I click Where here, it shows all the toolboxes that came with our MATLAB. If you buy yourself a student version of MATLAB, that's less than 100 euro, I think, and it comes with more toolboxes, but it has some limitations of how big matrices you can handle. But believe me that we are not exceeding that limit. Okay, if you want to still work on your own computer but want to save some money, there's also Octave, a SourceForge. You can download it from SourceForge. It's a GNU general public license tool. It's okay. It just does not have these nice toolboxes like signal processing toolbox. They say similar toolbox, but or package, but not exactly that one. And a couple of others are also totally different. For example, we are also using the control toolbox, but anyways, I have a note somewhere on the exercise, I think, how to basically tune your own Octave if you want to use that one. And this is totally doable also with Octave. Okay, good. So about the environment, I kind of tuned this one, but most of things happens on the command window. So you just write a command and something magic happens. Another one, there's also command history. So basically, well, if it looks like that, it's hard to see from the back row. Let me close clear that one. Okay, I try to keep my stuff about that line, but in any case, there is also the command history, and I will download this upload this command history after this nice show. Then the next one here, I think you have the current folder here. I don't find this one very useful when we are using only one folder. Okay, so basically what you should do first is to select the current folder, for example, exercise 1 or something like that. And yes, you can use also your network drive there. Okay, and this actually shows the workspace, meaning the variables, what we have been using. Okay, some really good things about MATLAB. The best part is probably help. On the other hand, we have big variety of toolboxes, so getting help on exactly the command what you want to use may be a little bit difficult. You find the correct kind of usage for a tool which appears on different toolboxes. In Octave, it's nice since all the functions, there's only one source for each function, and then you can actually just Google Octave and then the function name help. That'll work. Okay, but let me show you some things like what would help on the first part of this one. How to create an index vector, how to use that vector to create delta and mu. How to actually use those indexes to sample a sinusoid or anything else. How to multiply signals, signal product. Okay. So this is the exercise. Welcome. One. Tutorial. As you can see, I haven't used to this yet. All right, I will sit down then. So, exercise 1 tutorial. So basically, first let's take a look at different ways of creating an index vector. Oh, vector. So basically, first rule is that never use single letter variables anywhere in the world. Okay, so that in that reason, I'll actually use 2 n's for this one. MATLAB is kind of nice program that you can override even the built-in functions or variables, like, for example, the most common letter on C programming language for a loop counter is I, which is also the imaginary unit. Okay, and you know, you can also use J, and override that one also. So after that, you cannot actually type the imaginary numbers here. So use double digits. Use double digits, at least. Okay, but anyways, so if you have a variable name and equal sign, then you're basically setting the variable. And here you could use, for example, this kind of techniques. -2, -1, 0, 1, 2, 3, 4, 5. Okay, so that will be just a legitimate way of creating index vector from -2 to +5. So from here to there. Where did I put my? Yeah. So -2, -1. Good. So index vector done. And press enter, and it actually shows the result vector here. Good. Although when you are doing this kind of typing by hand, you might actually miss 1 digit there, and then that might cause some trouble. Or if there are, say, 10,000 points, it might get a little bit boring at some point. So you can also use auto-indexing. So this is exactly the same thing, from -2 to +5. And putting the semicolon at the end actually suppresses the printout. And then comment. Comment can be anywhere after the semicolon actually. Well, it ends the line in any case, so don't put comments at the middle of the stuff, it doesn't work. So basically this is from -2 to 5, and this has step size is 1. Okay, but as you can see from the workspace window, it didn't change at all the contents of my variable nn. Good. So those are the two methods basically how to create index vector. Adding values to a vector is also simple. For example, if you want to then add one more value to old one, for example, add number 6 there, you just basically combine these vectors, vector nn and then scalar value 6, or even say vector like that one. Now basically my nn equals to -2 to number 7. So combining different things together, you just put these brackets and put whatever you want there. Well, this is already that way. So you have scalars, meaning 1 by 1 matrices on a row like that. All right. So now we have indexes. Now we can actually produce, for example, delta function. Well, this is the discrete delta. So dd equals, just for fun, I put this one on parentheses, nn, and then we test if nn is equal to 0. Okay, so 2 equal signs means that this is a test. And what is returned from that is a logic level, 0 or 1. Actually, no, not true. It returns true or false vector. To basically return values, 0s and 1s, you need to do the casting to double. Double values are actually, double precision floating point values are the native values for any variable in MATLAB. So testing if nn is 0 and casting it to double precision floating point. There. So now we have nn and dd there. Good. Next step, how to make the picture. How can I actually make this one here as a figure? Plotting things. I could use plot function, but since this is sampled data with a small data set, I would prefer using stem instead. So stem, and as you can see, if you leave it like that, then it starts to give you some hints how to use it. I'm using the second method, so basically it's a stem of xx information, xx is or nn, and then the y information is d. There. So this is the stem plot of sampled data. There we go. If you were using Octave, the first plotting command actually may take even 1 minute, depending on your computer, since it does all kind of stuff there before starting. And you may actually need to tweak your graphics method on Octave. But anyways, so yeah, that's a picture. But I'm not too happy about it. So basically, you should let the data touch that box there. So if you want to clean it a little bit, my favorite is actually to use these commands like axis, and there you just have the limits, xlimit, xmin, xmax, ymin, ymax. You can also seek for more help, by the way. If you are not sure how to use a command, look for more help. Or just say help axis, it will give you the same thing, or doc axis. I'll show you those. But anyways, first I need, let's see, for example, minus 2.0 is the first one. By the way, decimal point here is point, period, not comma. All right, so maybe it's that up to 7.5 and minus 0.1 to 1.1, and that forces the axis to go, a little bit farther away. Then of course you need to put there the titles and the legends, axis information. In MATLAB you can also basically start the show plot tool and you use graphic interface to set up these values, but my favorite actually is to use, whoa, this probably doesn't work too well. Whoop. Okay. My favorite is to use the commands. So xlabel index. If you want to put more commands, either comma or semicolon actually works there. Ylabel, so in one line, and string is, for example, value, and title, example. And let's take a quick look at the figure. Okay, yeah, so it's just like that. How to copy this one to your answer window? Basically, what you can do is, to copy figure might actually work. Let's try it. It depends on the graphics drivers and the version of MATLAB. Let's try the copy figure and then just go to the exercise template. Let's see, does it work? Paste. Yes, it does. It probably does work, but reload. No, it didn't. Didn't do anything. So okay. So basically, at least on this computer, on Windows 10 and the latest MATLAB, it does work, but not on this one. So what you can actually do is to do the printing or save. Let's see, generate save as. Okay, there we go. Not as figure, but well, Windows bitmap or PNG, portable network graphics would work the best. So portable network graphics goes, well, and then maybe not untitled, but some other name. Figure 1. My favorite place is downloads. There. And now I can actually go and copy paste that one. There we go. Maybe this one works. Yep. Yes, it does. So, although it went to the wrong place, but all right. Okay. Let's figure out. So that's how you basically do it. So you make first the portable network graphics file from your figure, and then you can download it as a part of your exercise. All right, good. All right, so this one was the delta function. It's quite obvious that actually then if you want to make the step function, it's rather easy. You basically check if the NN is greater than or equal to 0. Oops. Okay. Or just for fun, I will do some delay. For example, delay by 3 points would mean mu of n minus 3. So, okay, mu of n minus 3 would start here. So basically, this one generates the step function which starts 3 time steps later. And casting to double again. So starts with 3 time step delay. There we go. And let's stem plot that one to SS stem plot. There we go. Yeah. So instead of starting at the origin, actually it starts at 0.3. Yes. Yeah, and this is quite low now. Let me pull it a little bit higher. Actually, you can see the with binoculars. Next time I'll bring some binoculars you can rent for a good price. So the command history is also here all the time. Okay. Maybe I should actually use some network drive so that the command history would show all the time there. But, well, maybe I'm lazy. Good. In any case, I could try to let me do something here. All right, so how low I can actually go here? Back row. Tell me when it's okay. The lowest line. Can you see the lowest line? Can you still see the lowest line? Okay, good. Now you can't anymore. Okay, good. There we go. So, step function, delta function, step function with the with some delay. Okay. Next step would be the sample a sinusoid, for example. And for that one, sampling a function. Maybe I shouldn't sample the sinusoid. I'll leave that to you. Okay, but a exponential, for example, exponential of minus t divided by some tau. So exponential the decay of signal. So practically this could be the high pass filter, RC high pass filter. Simple. And tau equals what? R times C, right? Good. For example, this is just an example how things could be done in MATLAB. So first, the resistor value, for example, resistor 1 value would be 1 kilo ohm. You can use this, IEEE notation. So 1E3 means 1000. Okay, and say 100 nanofards, E minus 9, right? There, wow, always use 2 digits on the variable. So I have 100 nanofarad capacitor and 1 kilo ohm resistor. Okay, now if we are having a digital sampling oscilloscope, how fast you should be actually sampling this one? You see these exponential decay nicely. Any ideas? Is 10,000 samples per second enough? Well, we can try. We can try. Let's see, R1 time. Oh, wait a minute. We can always calculate. So this would be the decay time. So that's 1 over 10,000. So yes, so that would be then that would be 1 over E already. So I think in order to make this one looks nice, we should sample it faster than that. Right. So now I'm just selecting the sampling rate. So Fs equals, say, 50,000. So 50K samples per second. And this is something what you just turned on your oscilloscope, or actually there you will set the division time. But practically it's relates to the sample per second. And then our sampling time would be 1 over Fs. Excellent. So that's a sample time. Look at that. And now we can actually do the sampling of this data set with existing index. Okay. Samples at n, indexes n, and sampling time of ts. Simple like that. E equals exponential of minus time equals actually n times ts. nn. So our time variable will be n times ts divided by r1 times c1. There we go. And of course, you would also have the amplitude there, some volts, but who cares about the volts? You do. Okay. So, well, standard, maybe we should have a amplitude there. So what is the usual amplitude what you would use to test a electronic circuit? Any suggestions? Is it always 1 volt amplitude, or what you would use for testing? Remember the first classes you took? Did you care about the actual amplitude of the signal? I didn't. I just measured it. Okay. Well, that's it. All right. So now I can show you what this would look like, but by the way, you can get the last commands by clicking up and down arrow, or start with the let me show that one. Oops. Let me show you that one. So if you basically click ST and then up arrow, you get these commands which started with ST. There we go. And okay, there's something wrong with this picture. Right. If this was a test of RC, and you would basically compare this one with your measurements, this have the data is starting from negative times. So usually you set the edge of your test vector starting at that point. But now we have a couple of extra points. And that's where you would use the heavy side function, step function. Okay, so we will use the step function. So EES equals EE dot times. So period times meaning element by element product, signal product. If you use this just multiplier there, then MATLAB would try to calculate the vector product and fails because those vectors must then, the dimensions must match, okay? But here we just need the element-wise product. So element-wise means dot operation, okay? Dot times, wait a minute, did I have the step function somewhere? Yes. SS actually is not the step function. I'll do it over. Double NN greater than equal to 0. I had the time delay on my SS. And this actually should start at time point. Oh, no, no. Of course, this one doesn't, but EES should. There we go. Now I have what I wanted. Good. Couple of pointers still there. So this is how you basically play with this different kind of functions and different kind of test vectors. And now you can sample. When you are sampling the sinusoid, remember to sample it correctly. So sine of something, but I'll let you to figure out it. It's not that bad. It just as well. This is worst. Generate exponential. What is that function all about? Well, you know it. But anyways, the sampling is very simple operation. If you have a function, you just have the the instead of the continuous time t, you would have n times ts as the sampling points. You need, so basically this n times ts is the sample times, simply. It's just a vector of sample times. Okay, nothing fancy about it. Next, basically, what we could do is to how about longer time samples, and then how to add some noise on it, and then some. Okay. Just a moment. I will just check. Okay. Data sequences generate. Okay, good. So basically you can do already 8 first exercises from those few lines and some thinking. And yes, you can work together. Preferably work together. When I started in real work, that was year 1997 in Vaisala. Have you heard of Vaisala? How many of you would like to work on our Vaisala? Raise your hands. Everyone. That's the best engineering the company in Finland. Seriously, it's the best. They really appreciate their engineers, and there are some people who have been there working for Vaisala for more than 30 years as engineers, and still working there as engineers. I would say that's a pretty good company then. Or they put something on the coffee, I don't know. Well, no, they don't spice up anything. But anyways, so when I started working there, then there were still some local gurus there who were kept, just happy on their boxes, and sometimes they came up with brilliant ideas. That was 1997, more than 20 years ago. Today, you must be able to work together with other engineers. No local gurus, not even in Vaisala anymore. No. No. They changed their minds and opinions, to avoid getting, laid off. Yes. So, yeah. So STEM. So next, let's take a look at longer time samples. Longer sampled. Sampled. Data vectors. Okay, now basically using the index method is fine, but actually there's also another way of generating this n times ts, and it works really well for longer time vectors. But before that one, let me change a little bit so that fs was 50,000. Let me mark it 44.1 kilo samples per second. So this is actually a CD quality sampling rate for PCM signals. So CD quality pulse tone modulation sampled signals, audio signals. Oops. Okay, standard, one of those Sound Blaster standards. So, and well, next step, I can actually calculate also the TS equals, again, 1 over Fs. So that's the sample time. Good. And now I can calculate actually longer time sample sets, like how about 1 second long thing. So my sample time vector would be then generated. Start from 0 second and use TS at the middle and then at the end time. So this actually means from 0 we step of TS to 1. And there I have about 44,101 double precision sample time vector. That one actually comes from the fact that I started from exactly the 0. I don't care. So this is 1 second long audio sample or audio sample times. Now I need a function to sample. So for example, I could use sinusoid. At the signal frequency of, is there anyone who plays any musical instrument anymore in the world? Anyone? Guitar players? Yes, excellent. You know what is note A in hertz? 440 hertz. 440. Note A, the basic A is 440 hertz. About. If you would play on a classical orchestra which has oboe, then you just hear what is the note of A in oboe and then basically tune every single instrument with that one. Oboe is hard to tune. what I have heard. I have heard actually that these oboes are which are used with the grand piano. They first tune the oboe and then the grand piano. Okay. But anyways, so sinusoid at a single frequency of 440 hertz. So let's see, I could generate it by, well, I could use it even now. So for example, like this. Do I have SS already? Yes, I do. Let's see. FO, like sound. FO equals some amplitude, just for fun, 0.25 as amplitude, times sine of 2 times pi times 440 hertz, and then just simple the sample time vector, TT. There we go. So this is a sound sample. It means that I can actually also here what it sounds like. So my samples and FS. I would if the loudspeakers were on. Okay. Nothing. I think the it's about wiring here. Try it out on your computer. This should actually sound the Can you hear anything? I'm not sure if there are any loudspeakers on these computers. It would be nice if we had. Oh yes, that's 440 hertz. Good. Okay, playback devices. Excellent. How did you do it? This is, well, nothing happens here. Good. So that's 440 hertz. I'm not going to play with this one. Next time I'll bring a better cable so I can run everything on my own laptop. All right, good. So, okay, that was 440 hertz and very dull sound. You can actually make it more realistic by adding some noise into it. Okay. So, for example, I can add some noise like NO equals random numbers of the size of SO. So what I'm doing, I'm adding a random number for every single data point like in here. It does have, oh. Huh, that's strange. It should be exactly the same. Okay. You might actually want to play those sounds, save the sound and then play it on different computer or something like that. It's you know, just relying on these loudspeakers, that's kind of lousy speaker. Okay, so this command here would generate me random numbers, normally distributed random numbers with standard deviation of 1 and mean 0 mean. Okay. However, let me put a little bit. What's happened there? The I will also scale it a little bit down. So, for example, since this one had the amplitude of 0.25, I put this, say, 0.1 times. Okay, so this is my signal, this is my noise, what I can calculate now. How about signal to noise ratio? Okay, on the exercise, I give you signal to noise ratio, and you should actually then calculate the noise amplitude from that one in order to add the requested amount of noise into your signal. But anyways, so the final signal here would be SN, simply SO plus NO. And you can hear it by playing the sound. I cannot hear anything here. Now, and settings are 72%, it should work. Yeah. So there's a sound which comes from the noise part and then still the 440 hertz that you can clearly hear. But anyways, so the signal to noise ratio for this one is in R equals, okay, now question, how to calculate signal to noise ratio if you know the noise amplitude and signal amplitude? A lot of smiley faces. Okay, how about 10 times 10 base logarithm of what? Power of signal, which is directly proportional to variance of signal, divided by variance of noise. Okay, so this is the magic behind how to calculate the signal to noise ratio. So variance of a signal is actually the same as the power of the signal. There we go. Oh, sorry. So we have 5 decibels of signal to noise ratio. 5 dB is not much, but actually, well, you can also play around with the noise and find out how well you can still hear the tone even with the when going into negative signal to noise ratios. Okay, good. So that's almost all for today. The only thing what is missing now is basically how to save this sound to SN. This sound to computer so that you can actually upload it to your favorite cloud service to include the link. That would be the part 10 of this signal exercise. First saving, let's see, help, WaveWrite, I think it's, okay, WaveWrite, write Microsoft Wave sound file has been removed. Use AudioWrite instead. Okay. Wow, that was a lot of. But anyways, there's always, if the help is always, printing everything on your command window. But if you want to check the same on nice browser, then basically write doc, which means document or for AudioWrite. Basically, we would be using this method. So AudioWrite file name, Y is our data, and then sample rate. Okay, and the output data type depends on the output file format, meaning that basically if you want your WAV file, then you just put the WAV as a part of your the file name. And well, wave file is just fine. So let's see. So audio write file name. Okay, this is just prime, not the double prime. And then, for example, exercise 1.wave, then our signal SNO and sample rate FS. There we go. Oh wow. What happened? Sorry, it was SN, not SNO. There we go. There we have one audio file just appeared on my working directory, which is that one, users AutoCAD documents MATLAB. Okay, how to publish that one is very simple. First, you need to go to your drive. By the way, you can also use some other, this other file service, as long as you can get a link to your file. So Dropbox is okay also for these files. Dropbox is not okay for the template, since that's Google Docs. And it's not really a file, it's in the cloud. All right, so for example, on this file, I have those things. I go and on the documents, MATLAB exercise 1.wave, when you copy that one into your directory, there. What you need also to do for this one, okay, let me put it like that. You need to actually share it before, you know, the link works. So if you click get shareable link, make sure that you actually also make this one so anyone can view it. Or in this case, it's also just to let, well, if you're using the Metropolia account, then anyone with Metropolia Ammattikorkeakoulu with the link can view. That's also okay. But my favorite way of sharing is that anyone with the link can view. Done. And link sharing copied. Back to this one. Provide a link. Ta-da. Control K and click clock. That's it. Then it's there. Okay. Some advice. When you're working this work together with some other students, or maximum 3, then when you have basically done everything and before submitting it, since one of you is making the submission, only one return per group, but before submitting, send the link to your friend so that he or she can actually check that everything works under that link. So remember those, I have this list of the typical errors. One typical error, oh, by the way, any of those typical errors will be worth of 1 point. So the first exercise, names of the students. Okay, if there's a missing name on this one, then I cannot give the points on the first round, and the second round there will be 1 less point. Okay, that's the first part where you can make a mistake worth of 1 point. Then of course this actually, one way of getting a reduction of points is to have exactly the same answer as some other group. Okay, I see. I didn't tell you about the SSS. So this is the last three non-zero digits of your student ID. When you are working on a group, please use the first student's student ID to make this SSS. So last three non-zero digits. So if I see exactly the same answer here as the other group, well, it's quite obvious that someone has been copying. You know, I studied in 80s. If you have some, you know, nice new ways of try to cheat the teacher, I know them all. I was one of those who invented them. Okay. Yeah, I'm so proud of it. Okay. Then about this one, when you're returning a link, make sure that it's a link that opens. If you do not put the if you just download your audio file somewhere and just take the link out of it, it does not necessarily yet open for everyone. So make sure that you have the link sharing on and you know, the appropriate way. All right. What else? I think that's the most important parts. And of course, about sharing of this file. When you return a link to this file, basically make sure that it works. The best way of checking is to get on this form, send me a copy of my response, open it up on, open the link on let's see, what is it? Incognito window, for example. Then it doesn't use any of your logging information there. So make sure that everything works when you return. Okay, so that's all for my show today. For the deadline for this exercise is next Monday morning when I'm starting my next show. So for this week, you have two things actually to do. Do the exercise and also take a look at next week's material. So next week we have systems. So today's exercise was kind of nice and light. It's about how to generate signals. Next week, how to present systems on MATLAB. It's a little bit heavier, not totally heavy stuff yet, but still, you know, rock and roll. All right. Any questions? If not, then have fun. See you next week.